August 17, 1943. Schweinfurt, Germany. 14:32 hours. A man is on fire. Not metaphorically, not symbolically. Staff Sergeant Roy Gibson, a 23-year-old kid from rural Indiana who fixed tractors before the war, is sitting in the ball turret of a B-17 Flying Fortress at 27,000 feet, and his oxygen line has just been severed by a 20mm cannon shell. The shell didn't kill him. The shell did something worse. It ignited the hydraulic fluid pooling near his feet, and now Roy Gibson is burning alive inside a glass and aluminum sphere, spinning beneath a crippled bomber over central Germany, 60 miles from the nearest Allied territory, with no way out and no one coming to save him. He survives. Barely. Third-degree burns across 40% of his body. 2 fingers amputated at the field hospital. 18 months of surgery. But Roy Gibson is one of the lucky ones, and that is the most terrifying sentence you will hear today, because on that single mission to Schweinfurt, the 8th Air Force lost 60 B-17. 600 men, in one afternoon. And the German fighters that did it flew home, refueled, rearmed, and were ready to do it again tomorrow. The Americans were losing the air war over Europe. Not slowly, not marginally, catastrophically. And somewhere in a factory in Farmingdale, New York, a solution was already being built. A solution so massive, so heavy, so absurdly over-engineered that Germany's finest aeronautical minds would dismiss it as a joke. A flying bathtub, an 8-ton embarrassment, a machine that every serious fighter pilot on both sides agreed could not possibly work. They were all wrong. By the time the war ended, this machine would destroy more German aircraft than any other fighter in American history. It would fly over 500,000 combat sorties. It would fire more than 135 million rounds of .50 caliber ammunition into the heart of the Third Reich. And it would do all of this because one company, one engine, and one philosophy of war decided that the rules of fighter design were not rules at all. They were suggestions. And America was done following them. This is the story of the P-47 Thunderbolt. And it starts not with a general, not with a politician, not with a hero whose name you already know. It starts with an engine. In 1937, America was not at war. America was watching from a distance as Spain tore itself apart, as China burned under Japanese bombs, as Europe stumbled toward a catastrophe it could already smell but refused to name. The United States Army Air Corps was flying biplanes. Not everywhere, not entirely, but enough to embarrass anyone paying attention. The fighter doctrine was built around nimble, lightweight aircraft that could dance around each other at low altitude in turning dogfights, lifted straight from the First World War playbook. The men at Pratt and Whitney in East Hartford, Connecticut, were not interested in that playbook. They were engineers. Specifically, they were engineers who had spent the previous decade building radial aircraft engines and learning with each iteration that the conventional wisdom about power and weight was incomplete. The conventional wisdom said that a bigger engine was a heavier engine, and a heavier engine meant a heavier aircraft, and a heavier aircraft was a slower, less maneuverable aircraft, and therefore a worse fighter. The logic was clean and simple and almost entirely correct. Almost. What the conventional wisdom missed was altitude. The engineers at Pratt and Whitney had noticed something. At high altitude, where the air was thin and cold and merciless engine power dropped off a cliff. Every piston engine suffered from this. As altitude increased and air density decreased, less oxygen reached the cylinders, combustion weakened, and power fell. A fighter that produced 1,000 horsepower at sea level might produce 600 horsepower at 25,000 feet. This meant that high-altitude combat was fundamentally different from low-altitude combat, and the fighter optimized for one was often useless at the other. The solution was supercharging. Force-feed compressed air into the engine regardless of ambient pressure, and you could maintain power at altitude. German engineers knew this. British engineers knew this. Everybody knew this. The difference was execution. Germany's supercharging technology was good. Britain's was better in some applications. Pratt and Whitney's was in another category entirely. The R2800 double Wasp began taking shape on drawing boards in 1937, and from the beginning it was an act of engineering aggression. 18 cylinders arranged in 2 radial rows of 9. Total displacement of 2,800 cubic inches, hence the designation. A 2-stage supercharging system with an intercooler between stages that cooled the compressed air before it entered the engine, increasing oxygen density and extracting every possible unit of power from the fuel mixture. The crankshaft alone was a masterpiece, a massive forging machined to tolerances of 1/1000th of an inch across its entire length, designed to withstand thousands of explosive combustion events per minute, without the vibration that destroyed lesser engines at high power settings. Early variants produced 2,000 horsepower. Later variants with water injection would produce over 2,600. This was not an engine. This was a controlled detonation contained inside a metal housing and pointed at the enemy. But an engine needs an airframe, and the airframe that Republic Aviation designed around the R2800 was by any conventional measure an act of insanity. The design team at Republic, led by Chief Engineer Alexander Kartveli, made a decision that horrified nearly everyone who heard it. They were not going to optimize the aircraft for turning performance. They were not going to chase the dogfighting metrics that defined every fighter evaluation in every air force in the world. They were going to build the smallest possible airframe that could surround the R2800 engine, carry enough fuel to be useful, arm it with enough guns to be lethal, and then protect the whole assembly with armor plate that would make it nearly impossible to kill. The result, when the prototype flew in 1941, weighed almost 13,000 pounds, fully loaded. Fully loaded. A Messerschmitt Bf-109 weighed roughly 6,000 pounds. A Focke-Wulf 190 weighed about 9,000 pounds. The P-47 Thunderbolt weighed as much as both of them combined, and then some. Fighter pilots who saw it for the first time called it the Juggernaut. They called it the Thunderbug. They called it the Flying Milk Bottle. Some called it unprintable things. The USAAF evaluation pilots who flew it first were not enthusiastic. The aircraft handled poorly at low altitude. It turned like a freight train. In any slow-speed maneuvering engagement below 10,000 feet, a competent German pilot in a Bf-109 would dismember it. The reports that came back from early testing were damaging. Multiple senior officers argued that the program should be canceled, that the money and aluminum and engineering hours would be better spent building more of what was already working. Lighter fighters, more agile fighters, fighters that played the game by the rules. What the skeptics were missing, what would not become clear until those early Thunderbolts reached England in the autumn of 1942 and began flying escort missions over occupied Europe, was that the rules had already changed. They just didn't know it yet. The 56th Fighter Group received their P-47s in January 1943 at Halesworth in Suffolk, and the pilots who flew them were by and large not pleased. These were men who had trained in P-40S and P-39S lighter aircraft with familiar handling characteristics. The Thunderbolt felt like flying a building. On takeoff, it accelerated reluctantly, burned through runway at an alarming rate, and climbed with the enthusiasm of a man who had just eaten a large meal. Early formation flights were exercises in humility. The aircraft's controls were heavy and imprecise at low speed, demanding physical strength and patience, rather than the light-fingered delicacy that made a skilled pilot feel alive. Colonel Hubert Zemke, commanding the 56th, was a pragmatist. He had survived enough to know that complaining about your equipment was a luxury that dead men could not afford. He told his pilots something that would prove prophetic. Stop trying to fly it like a P-40. Stop trying to turn it. Stop trying to dogfight. This aircraft is not built for any of those things. Take it to altitude, climb above the enemy, then come straight down at full throttle and shoot. One pass. Pull out. Climb back up. Do it again. If anyone gives chase, let them. They cannot follow you. This was not intuitive. Every instinct built into a fighter pilot through training said engage, pursue, dominate, never let the enemy escape. Zemke was asking his pilots to do something psychologically brutal. He was asking them to make a kill and then run. Not because they were afraid, because running was winning. The first major test came on April 15, 1943, when 16 P-47s from the 56th encountered a formation of Focke-Wulf 190s over the Dutch coast at 28,000 feet. The Germans had altitude advantage, initially diving to attack a formation of B-17Es below. The Thunderbolts pushed their throttles to the wall and climbed to intercept on the pullout. What happened in the next 4 minutes would be studied in briefing rooms from England to Berlin. The German pilots, experienced veterans with hundreds of combat hours, tried to engage the Thunderbolts in turning combat as they had engaged every other American fighter. The Thunderbolts did not turn. They dove. At 400 miles per hour. At 450. The FW-190 pilots trained to follow pushed their own aircraft into pursuit dives and immediately discovered that the massive American fighters were simply pulling away. At 480 miles per hour, where the Focke-Wulf airframe began to suffer control flutter, and the pilot had to reduce throttle to prevent structural failure. The P-47 was still accelerating, still stable, its massive wing spar absorbing forces that would have destroyed a lighter aircraft. One German pilot followed a Thunderbolt to 5,000 feet before finally pulling out, watching the American fighter disappear toward the channel at a speed he could not match and dared not pursue further. 3 FW-190s were destroyed. 1 P-47 was damaged. The pilot brought it home. The after-action report that Zemke filed that evening contained a sentence that would echo through 8th Air Force Command for the next 2 years. Quote, "The aircraft performs as advertised above 15,000 feet and exceeds all advertised specifications in the dive. Exceeds all advertised specifications." That sentence landed in Luftwaffe intelligence, within weeks passed through captured documents and interrogated prisoners, and it caused the first serious concern at fighter command about this new American machine. Because the Germans had read the specifications. They had reviewed what American aviation journals and pre-war technical publications said about the Thunderbolt. They had done the mathematics. The aircraft was too heavy. It was too big. It was aerodynamically mediocre. Their calculations showed conclusively that it should not be able to do what pilots were now reporting it was doing. The calculations were correct. The conclusions were wrong. What German intelligence had not accounted for was the R2800 engine running at power settings that its designers had been told were unsafe, channeled through a propeller 13 feet in diameter, that bit the thin air at high altitude with an efficiency no European propeller system had achieved, fed by a supercharging system that actually increased relative power output as altitude rose rather than fighting a losing battle against thin air. The P-47 at 30,000 feet was not the same aircraft as the P-47 at 10,000 feet. It was something meaner, something faster, something that played by rules it had written itself. In June 1943, a Thunderbolt from the 56th Fighter Group made a forced landing near Saint-Omer after taking flak damage. The aircraft was captured largely intact. German test pilots and engineers at the Luftwaffe Evaluation Center at Rechlin had their first opportunity to examine what they were up against. Senior test pilot Oberleutnant Hans-Werner Lerche flew the aircraft through a full evaluation sequence, including the high-altitude performance runs and dive tests that had made the aircraft notorious. His report, when it reached Luftwaffe headquarters, described an aircraft that handled like a truck on the ground and transformed into something else entirely above 10,000 feet. He performed dives past 500 miles per hour in which the P-47 remained stable and controllable, while German fighters at the same speed risked catastrophic structural failure. He climbed it to 40,000 feet and found the controls still responsive. He came back and told them what they were facing. But knowing what you are facing and knowing how to stop it are two entirely different problems. And in the summer of 1943, Germany had not solved the second problem. Not yet. Not ever. At airfields across occupied Europe, Luftwaffe pilots were beginning to discuss the Thunderbolt in terms that would have been unthinkable a year earlier. Not with contempt, not with dismissal, with something older and colder and far more dangerous to a fighting force than any technical disadvantage. With fear. Because fear, once it enters a pilot's cockpit at altitude, does not leave. And in Part 2, we will see what happens when that fear meets the full weight of American industrial production coming online at a scale that would make even the most optimistic Allied planner question whether the numbers could possibly be real, and how a single engine built by women who had never seen an aircraft factory 18 months earlier would become the heartbeat of air superiority over the skies of Nazi Germany. Part 1 ended with a captured Thunderbolt on a German test field and a Luftwaffe pilot climbing out of the cockpit with something he had not expected to feel. Not contempt. Not relief. Something closer to dread. The P-47 had performed beyond every specification Germany's engineers said was possible for an aircraft that heavy, that large, that fundamentally overbuilt by every metric European aviation had used for a decade. And the report that went up through channels to Luftwaffe High Command contained a warning that nobody at the top wanted to hear. This American machine was not a temporary problem. It was a structural one. But here is the number that nobody was talking about in the summer of 1943, the number that should have ended the debate before it started. In August of that year, the 8th Air Force had fewer than 200 operational P-47s over Europe. 200 fighters for a campaign that required escorting hundreds of bombers across hundreds of miles of hostile airspace every single day the weather permitted. It was nowhere near enough. And the men running the air war in England knew it. The question was not whether the Thunderbolt could fight. April and June had answered that. The question was whether America could build them fast enough to matter before the Luftwaffe bled the bomber offensive to death. And that question lived inside a factory in Farmingdale, New York, where a man named Robert Woods was about to have the worst meeting of his career. Woods was not a general. He was not a decorated combat pilot or a politician with powerful connections. He was a production superintendent, 41 years old, former machinist. The kind of man who had worked his way up from the shop floor by understanding the difference between what an engineer draws on paper and what a human being can actually build under pressure in real time. He had been at Republic Aviation since 1939. He knew the R2800 engine better than almost anyone outside of Pratt and Whitney. And in August 1943, he walked into a conference room at Wright Field in Dayton, Ohio, and told Brigadier General Harold McClelland that the current production schedule was going to get American pilots killed. McClelland was not a man who enjoyed being told things by production superintendents. He had spent 20 years in the Army Air Corps, building a career on the assumption that his judgment about aircraft requirements was superior to that of civilians, and nothing in his experience had seriously challenged that assumption. He sat at the head of a table, surrounded by procurement officers, and looked at Woods the way experienced bureaucrats look at people who are about to make their lives complicated. Woods put his numbers on the table. Republic was producing approximately 190 Thunderbolts per month. The combat groups in England needed at minimum 300 per month just to maintain operational strength, accounting for combat losses, accidents, and the attrition of high-intensity operations. To build toward actual air superiority, the number needed to reach 400 per month within 6 months. Woods had a plan to get there. It required authorization to expand the Evansville, Indiana plant, immediately approval to bring on a second shift of workers across both facilities, and a procurement order for raw materials at a scale that would require bypassing the standard requisition process. McClelland looked at him for a long moment. Then he said something that Woods would repeat in interviews for the rest of his life. He said, "Mr. Woods, the Army Air Forces does not reorganize its procurement process because a factory foreman is in a hurry." Woods did not leave the building. He sat in a hallway outside the conference room for 3 hours, until he got a second meeting, this time with a colonel named Edward Chickering, who ran logistics for the 8th Air Force and had spent the previous 4 months watching his bomber groups return from missions with fewer and fewer aircraft and more dead. Chickering had numbers too. His numbers were the kind that ended careers and started congressional investigations. In the 6 months between February and August 1943, the 8th Air Force had lost 440 heavy bombers, over 4,000 men. Most of them died because there were not enough fighter escorts to keep German interceptors away from the formations. Chickering listened to Woods for 20 minutes. Then he picked up a telephone. What happened over the next 72 hours was the American military bureaucracy moving at a speed it rarely achieved and could never fully explain afterward. Chickering called a man he knew at the War Production Board. That man called someone at the Office of Production Management. Approvals that normally took 6 to 8 weeks moved in days. Not because the system was efficient, because the alternative was losing the air war over Europe in the autumn of 1943, and enough people in enough rooms understood that with sufficient clarity to stop protecting their processes and start solving the problem. By September 15, 1943, the Evansville plant had authorization to hire 3,400 additional workers. The problem was that 3,400 additional workers did not exist in Evansville, Indiana, with aircraft manufacturing experience. They did not exist anywhere in that region with any manufacturing experience relevant to building fighter planes. The workers who showed up to the hiring lines in September and October of 1943 were farmers finishing their harvest, women whose husbands were overseas men too old for military service, teenagers who had never operated anything more complicated than a hay baler. Woods flew to Evansville and spent 3 weeks on the factory floor personally redesigning the assembly process. This was the idea that the engineers at the main Farmingdale plant had called in private, and with some condescension, a simplification scheme. The original R2800 assembly process required a skilled machinist to fit each component individually, checking tolerances by hand and making micro-adjustments based on accumulated experience. It was the way aircraft engines had always been built. It produced excellent engines when you had excellent machinists. It produced nothing at scale when your workforce had been in a cornfield 6 weeks ago. Woods broke the engine assembly into 340 discrete operations. Each operation was documented with photographs, not engineering drawings. Each operation was performed by one person who did nothing else. The fixtures that held components in position during assembly were redesigned so that a correctly manufactured part would fit in only one orientation, making incorrect assembly physically impossible. Quality inspection happened at every stage, rather than at the end, catching errors at the point of minimum cost, rather than after 50 hours of additional work had been invested. The first engines off the Evansville line in November 1943 were tested against engines from the Farmingdale facility. The results went to Wright Field in a report that nobody at procurement had requested, and everyone read anyway. Evansville engines were performing within 1% of Farmingdale engines on power output, temperature management, and durability cycles. They were being built in 12% less time, by workers with an average of 9 weeks of manufacturing experience. McClelland did not apologize. Senior officers rarely did. But in December 1943, he signed the authorization for a third production line at Evansville and approved the material requisitions that Woods had originally requested in August. The production numbers that followed were the kind that made German intelligence officers question their own sources. In January 1944, combined output from both facilities reached 330 Thunderbolts. In February, 370. By April, the number crossed 400. Pratt and Whitney's R2800 production feeding not only P-47s, but also F-6F Hellcats and other aircraft types, reached 4,000 engines per month by mid-1944. 4,000 engines per month from a workforce that had not existed as an industrial labor force 3 years earlier. At Luftwaffe Fighter Command, The intelligence reports arriving through the autumn and winter of 1943 described this production acceleration in terms that grew increasingly alarmed with each successive document. The initial assessments had predicted that American industrial expansion would plateau. That was the experience of every major industrial power that had attempted rapid military production scale-up. There was always a ceiling imposed by raw material availability, skilled labor constraints, tooling capacity, or logistics. Germany's own experience confirmed this. Every attempt to dramatically increase fighter production had run into one constraint or another that flattened the growth curve. The Americans were not flattening. Every report suggested the curve was still climbing. In January 1944, the 56th Fighter Group flew its first mission with the full complement of P-47s that Zemke had been requesting since the previous spring. 48 Thunderbolts in close escort formation with a group of B-17s bound for industrial targets in western Germany. The Luftwaffe sent up 2 Gruppen of FW-19OS to intercept. The engagement lasted 11 minutes. The Germans lost 14 aircraft. The Americans lost 2, both from flak rather than fighter action. The after-action reports from both sides agreed on the basic mathematics of the engagement. The Germans had committed 60 fighters against a P-47 escort and walked away with a casualty ratio that, if sustained, would destroy their fighter force in a matter of months. It was not one battle. It was never one battle. It was the accumulation of hundreds of such engagements across the winter and spring of 1944, each one extracting losses that Germany's shrinking pilot pool and straining industrial base could not replace at the rate they were occurring. The Thunderbolts that Zemke's pilots flew in January 1944 were not tactically different from the aircraft they had flown in April 1943. The tactics were the same. The engine was the same. What had changed was the number: 48 aircraft instead of 16, 300 instead of 40. The mathematics of attrition do not shift gradually. They shift at thresholds, and America had crossed one. But in the spring of 1944, something else was happening, something that the production reports and the combat statistics could not fully capture. German intelligence had been watching the P-47 production numbers with focused attention. They had reached a conclusion that was tactically logical and strategically catastrophic. If they could not match the Americans in the air, they would go after the source. Not the factories. Not yet. Something closer. Something more vulnerable. They had identified specific supply chain dependencies in the R2800 production process. Critical alloys. Specialized tooling. Subcontractors with no redundancy. And they had assets in place to act on that information. The production miracle that Woods had built in Evansville had a weakness. A single weakness. And in the spring of 1944, German intelligence knew exactly what it was. The real war was just beginning. The Thunderbolt had gone from prototype to production nightmare to combat weapon in less than 2 years. By the winter of 1943, the 56th Fighter Group was destroying German aircraft at ratios that procurement officers in Washington struggled to believe without the after-action reports in front of them. The Evansville plant was climbing toward 400 aircraft per month. And at the end of Part 2, German intelligence had identified a specific vulnerability in the R2800 production chain, a single point of failure that, if exploited, could slow the entire American air campaign over Europe. What they did with that intelligence, and what happened next, is the part of this story that most history books skip entirely. In February 1944, Luftwaffe Fighter Command convened an emergency assessment at Karenhall Hermann Göring's estate, northeast of Berlin. The officers who gathered around that table had a combined total of over 2,000 combat missions between them. They were not men who frightened easily. But the loss statistics from the previous 6 months had produced a document that nobody in that room wanted to read aloud, and everyone had already memorized. In the last quarter of 1943, Luftwaffe fighter units on the Western Front had lost 1,097 pilots killed or missing. That was not a quarterly figure from a war of attrition. That was systemic collapse, measured in human beings. The replacement pilots arriving at frontline units carried logbooks showing 150 to 180 total flight hours. In 1940, the minimum acceptable standard had been 400. They were sending children against the men who flew Thunderbolts, and the mathematics were not improving. General Adolf Galland, who commanded the fighter arm, stood at the front of that room and said something that no senior Luftwaffe officer had been willing to say publicly until that moment. The P-47 was not a tactical problem. It was a production problem. Germany could not build fighters fast enough to replace what the Thunderbolts were destroying, and until that equation changed, no tactical adjustment would alter the strategic outcome. The room was quiet for a long time after he finished. The counter-strategy that emerged from Hall had two components. The first was tactical. German fighters would stop engaging P-47 escorts directly whenever possible, concentrating instead on fast single-pass attacks against the bomber formations, before the escorts could react, then diving away at full throttle to avoid pursuit. This preserved pilots at the cost of bomber kills, an uncomfortable trade-off, but a survivable one. The second component was more aggressive. German intelligence assets in neutral countries had traced specific raw material shipments feeding the R2800 production line to a single specialized alloy supplier in Connecticut. Disrupt that supply chain, and Pratt and Whitney's production would fall. The operation was authorized in March 1944. It failed within 11 days when American counterintelligence rolled up the network. But the attempt revealed something important about how desperate Germany's situation had become. They were no longer trying to win the air war. They were trying to slow it down. Back in Farmingdale, the crisis that nobody in Washington wanted to acknowledge was already happening, and it had nothing to do with German sabotage. It was a metallurgical problem. In December 1943, the quality control team at Evansville flagged an anomaly in a batch of turbo supercharger housings. The exotic nickel alloy used in the housings, which had to withstand temperatures exceeding 1,600 degrees Fahrenheit, while spinning at over 20,000 revolutions per minute, was showing microfractures at a rate 3 times higher than the Farmingdale baseline. The fractures were not immediately catastrophic. An engine would run normally for 50 to 80 hours before the housing failed. In combat where missions ran 4 to 6 hours, that meant a pilot could fly 15 to 20 missions before his supercharger failed at altitude over Germany. 15 to 20 missions was not a safety margin. It was a death sentence with a delayed fuse. Woods flew to Evansville on 72 hours' notice. The engineering team had already identified the probable cause. The secondary alloy supplier brought online to meet the expanded production schedule was using a slightly different heat treatment process that produced housings within the dimensional tolerances on paper, but with internal grain structures that weakened under sustained thermal cycling. The fix was not complicated. It required a process modification at the supplier level and a revised inspection protocol. But implementing it meant slowing the Evansville line by an estimated 18% for 6 to 8 weeks, while the change was validated and the existing suspect inventory was quarantined. Colonel Chickering called Woods from England. The conversation lasted 4 minutes. Chickering's position was direct. Slow the line. Find every housing from the affected batch. Ground the aircraft if necessary. A dead pilot and a lost aircraft cost more than 6 weeks of reduced output, and there was no version of this war in which America won by sending men to die in preventable accidents over the Rhine Valley. Woods made the call. The Evansville line ran at reduced capacity through January and February of 1944. The corrected housings began shipping in March. The failure rate dropped to below 0.3% within 2 production cycles. Nobody celebrated. They moved on. Then came February 20th, 1944. The week that history would call Big Week. The 8th Air Force had been planning Operation Argument for months, a sustained series of coordinated attacks against the core of Germany's aircraft manufacturing capacity, ball-bearing plants, engine factories, assembly facilities, The intelligence estimate was blunt. If the raids succeeded and Germany's fighter production was reduced by 40% or more, the Luftwaffe could not sustain operations at current tempo beyond the autumn. If the raids failed, if the bomber losses reached the catastrophic levels of Schweinfurt in October 1943, the political will to continue the strategic bombing campaign might not survive. The P-47s would be the shield. On February 20th, 1943, at 0630 hours, 16 combat groups launched from airfields across East Anglia. Over 800 B-17 and B-24 in the bomber stream. Fighter escort coverage provided by P-47 Thunderbolts, P-38 Lightnings, and for the first time in significant numbers, P-51 Mustangs with drop tanks capable of reaching Berlin. The Thunderbolts would handle the middle portion of the route, handing off to Mustangs for the deep penetration and picking up the bombers again on the withdrawal. The Luftwaffe rose to meet them. They had no choice. Allowing uncontested bombing of the aircraft factories was accepting defeat at one remove. Every available fighter group in the Western Defense Zone was scrambled. At 25,000 feet over the Dutch border, the first major engagement began. The German formation, approximately 80 FW-190s and BF-109s, came up fast from the south in a climbing turn, trying to get above the P-47 escort and dive through the formation before the Thunderbolts could react. The tactic had worked in October. It did not work on February 20th. The 56th Fighter Group was already at 30,000 feet. Zemke had positioned his pilots above the expected intercept altitude, burning extra fuel to buy the altitude advantage. When the German formation reached 26,000 feet, still climbing, still trying to get above the escorts, the Thunderbolts were already diving. Full throttle. 400 miles per hour. 450. 500 in the dive. 8. 50 caliber guns per aircraft. 425 rounds per gun, firing at over 800 rounds per minute each. The engagement lasted less than 4 minutes. It looked nothing like a dogfight. It looked like an industrial process. The Thunderbolts dove through the German formation from above, firing as they passed, pulling out below, and then using their speed to zoom back up to altitude before the scattered Germans could organize a pursuit. The FW-190 pilots, who tried to follow the P-47s into the dive, lasted approximately 30 seconds before their airframes began to shake at speeds the aircraft was never designed to sustain. 12 German fighters went down in those 4 minutes. 2 more collided while maneuvering to avoid attack. 3 P-47s took hits. All 3 made it back to England. The bomber stream continued east, largely unmolested for the next 40 minutes. When the Thunderbolts handed off the escort to the Mustangs over the German border, the bomber formation was intact. The targets that day were the Messerschmitt assembly plants at Regensburg and Bernburg and the Focke-Wulf facilities at Oschersleben. The bombing accuracy achieved on February 20th reduced production at those facilities by an estimated 35% for the following 8 weeks. Over the 6 days of Big Week, the 8th Air Force lost 137 heavy bombers. A significant number, a painful number, but not the catastrophic 20% plus loss rate of Schweinfurt. The Luftwaffe lost 355 fighters destroyed and another 200 damaged beyond immediate repair. More critically, they lost 100 pilots, killed 57 wounded, and 28 captured. Against a pilot replacement rate that was already running 2,500 short of annual losses, those 6 days represented a wound the German fighter arm could not close. Gallen's after-action assessment went to Göring in early March. It contained a sentence that functions as an epitaph for the Luftwaffe's strategic position in the air war. He wrote that the fighter force could no longer guarantee the defense of German industrial centers against coordinated American attacks with heavy fighter escort, and that any strategy predicated on halting the bombing campaign through air-to-air combat alone was no longer viable. The P-47 was not solely responsible for Big Week's success. The Mustang's range had changed the calculus of deep penetration raids. The sheer numbers of aircraft the Americans could now put in the air simultaneously were a factor no single aircraft type could fully account for. But the Thunderbolt's performance over the Dutch border on the morning of February 20th had demonstrated something that would shape every remaining air operation over Europe. When American fighter pilots had altitude position, and numbers German fighters died at ratios that no amount of tactical adjustment could reverse. The Thunderbolt had not beaten the Luftwaffe through elegance or refinement. It had beaten them the way a factory beats a craftsman. Systematically. Relentlessly. At a scale the other side could not match. By March 1944, new pilots arriving at the 56th Fighter Group were being told something that would have seemed absurd 18 months earlier. The P-47 was not their limitation. Their limitation was their own discipline. The aircraft could do things they had not yet learned to trust. Their job was to learn to trust it before Germany figured out an answer. Germany never figured out an answer. But the man who had reorganized the Evansville production line, who had grounded suspect aircraft, who had sat in a hallway at Wright Field for 3 hours, waiting for a second meeting, Robert Woods did not receive a medal. He did not give speeches. He went back to the factory floor and kept building engines. And what happened to him after the war? And what happened to the men and women who built 15,683 Thunderbolts in 4 years is a story that almost nobody knows. That story is part 4. From a factory floor in Farmingdale to the skies over the Reich, the story of the P-47 Thunderbolt moved in 4 years from a drawing that experts called aerodynamically irresponsible to the most prolific fighter in American aviation history. Part 1 showed you the machine that shouldn't have worked. Part 2 showed you the production miracle that built it at scale. Part 3 showed you what happened when it met the Luftwaffe in sustained combat over the heart of Germany. The cliffhanger at the end of Part 3 asked a question that combat statistics cannot answer. What happened to the people behind it? What happened to Robert Woods? To the women on the Evansville assembly lines? To the pilots who trusted their lives to an aircraft that everyone else had dismissed? And what is the real cost of being right when the institution around you is certain you are wrong? Because success, as it turns out, does not always look the way you expect it to when you are standing in a hallway at Wright Field, waiting for a second meeting that nobody owes you. Robert Woods returned to civilian life in 1946 without a medal, without a ceremony, and without a biography. He went back to Republic Aviation as a senior production consultant, a title that meant roughly what it sounds like, a man whose expertise was indispensable as long as there were aircraft to build and quietly surplus once the contracts wound down. He retired in 1958. He gave no speeches at retirement dinners that have been recorded. He did not write a memoir. He did not appear in the post-war documentaries that celebrated the air war over Europe with clean narratives and clearly identified heroes. The production superintendent who had redesigned the Evansville assembly process grounded suspect aircraft over the objection of schedule pressures and sat in a hallway for 3 hours until he got the meeting that changed the output curve of American fighter production in late 1943, spent his final years in Connecticut, near enough to the Pratt and Whitney facility in East Hartford, to have driven past it on the way to wherever he bought his groceries. He knew what had been built there. He knew what it had done. Whether that knowledge was sufficient compensation for the absence of public recognition is a question nobody thought to ask him while he was alive to answer. The women of the Evansville plant fared similarly in the historical record, which is to say, they largely vanished from it. At peak production in 1944, roughly 42% of the Evansville workforce was female. These were women who had learned to machine turbo supercharger housings to tolerances of 1/1000th of an inch, who had trained on assembly operations that required more precision than most manufacturing work available to civilians before the war, and who met or exceeded the quality standards set by the experienced machinists they worked alongside. When the war ended and the contracts canceled, they were thanked for their service and returned to the category of people who did not build aircraft engines. Some went back to teaching. Some went back to the homes they had left. A few stayed in manufacturing roles where the industries would accept them. The institutional memory of what they had accomplished at Evansville lived primarily in production records and engineering assessments that nobody outside the industry read. Brigadier General McClelland, the procurement officer who had told Woods that the Army Air Forces did not reorganize its processes because a factory foreman was in a hurry, retired in 1951 with commendations for his contributions to wartime procurement efficiency. This is not presented as injustice. It is presented as the ordinary texture of institutional history where credit flows upward and expertise flows wherever the paperwork directs it. Colonel Chickering, who had called Woods from England and told him to slow the line and find every suspect housing died in a training accident in 1947. He was 44 years old. His personnel file notes his contributions to 8th Air Force logistics without specifics. The legacy that none of these people received individual credit for was nevertheless enormous, and the numbers that describe it are the kind that require a moment of stillness before they fully register. The P-47 Thunderbolt flew 546,000 combat sorties during the Second World War. It destroyed 3,916 enemy aircraft in air-to-air combat. It dropped 132,000 tons of bombs and fired 135 million rounds of .50 caliber ammunition against ground targets. 15,683 Thunderbolts were built across both facilities before production ended. The R-2800 engine that powered them, produced by workers who had never built an aircraft engine before Pearl Harbor, maintained operational reliability rates above 95% throughout the campaign. In the industrial mathematics of the air war, that reliability rate was not a footnote. It was the foundation on which everything else rested. The R-2800 itself did not retire with the Thunderbolt. The engine went on to power the F-6F Hellcat, which destroyed more Japanese aircraft in the Pacific than any other naval fighter. It powered the F-4U Corsair, which flew combat missions in 3 separate wars across 20 years. It powered the A-26 Invader attack bomber, which was still flying combat missions in Vietnam in 1969, more than 2 decades after the Evansville plant built its last Thunderbolt. The engine's fundamental architecture, 2 rows of 9 cylinders, 2-stage, supercharging with intercooling redundant ignition systems, manufacturing tolerances that left no room for craft-based judgment at the assembly stage, became the template against which subsequent American radial engine development was measured. Pratt and Whitney produced over 125,000 R-2800 engines before production finally ended. By any reasonable definition, it is the most successful aircraft piston engine in American history. The assembly methodology that Woods developed at Evansville, breaking complex processes into discrete documented operations, performed by semi-skilled workers using fixtures designed to make incorrect assembly impossible, did not stay in aircraft manufacturing. The same principles appeared in consumer electronics production in the 1950s and 1960s, in automotive manufacturing refinements throughout the post-war decades, and eventually in the precision assembly protocols used by contract manufacturers building components for industries that did not exist when the Evansville plant was running 3 shifts a day. Woods did not receive attribution for this transfer of methodology. The ideas moved the way practical knowledge usually moves through the people who carried them out of one context and applied them in another, with the original source becoming progressively harder to trace. The deeper lesson, the one that the technical legacy cannot fully contain, is about the relationship between institutional certainty and operational reality. McClelland was not a foolish man. His skepticism about reorganizing procurement processes on the request of a production superintendent had a rational basis rooted in experience. Organizations that reorganize their processes every time someone with a compelling argument appears in a hallway do not function effectively. The conservatism that frustrated Woods in August 1943 was the same conservatism that had produced the procurement infrastructure that was building hundreds of aircraft per month in the first place. The institution was not wrong in general. It was wrong in this specific instance, at this specific moment, when the cost of maintaining standard process exceeded the cost of making an exception. Recognizing that distinction in real time under pressure with incomplete information is harder than any retrospective account makes it appear. The Thunderbolt story belongs to a pattern that recurs throughout the history of military innovation. The proximity fuse, developed in secrecy and first deployed in naval anti-aircraft ammunition in 1943, was considered so operationally significant that its existence was classified for years out of fear that captured rounds would allow Germany to copy it. The technology involved a radio transmitter and receiver small enough to fit inside an artillery shell that could survive being fired from a gun, a specification that everyone with relevant expertise said was physically impossible until the engineers at the Applied Physics Laboratory built one. The cavity magnetron, the component that made practical radar possible, was brought to the United States from Britain in 1940, inside a metal box carried by a physicist on a commercial flight, because it was considered too important to risk losing on a military transport. The men who evaluated it at MIT's radiation laboratory included several who had publicly stated that miniaturized high-frequency radar was not achievable with available technology. In each case, the pattern was the same. Expert consensus based on existing parameters. An idea that violated those parameters. Institutional resistance proportional to the confidence of the consensus. A small group that proceeded anyway. Results that required the consensus to be revised. The detail that most documentary accounts of the P-47 omit, the one that functions as both twist and completion for this story, is what happened to the first production Thunderbolt off the Farmingdale line in 1942. Aircraft serial number 4, 1-5895. The first P-47B, accepted by the Army Air Forces, was used as a ground trainer after developing engine problems that made it unsuitable for flight operations. It was struck from the inventory records in 1944 and presumably scrapped its aluminum recycled into subsequent production. The first of 15,683 Thunderbolts did not survive the war it helped to win. It was consumed by the industrial process it had initiated. There is something in that fact that resists easy interpretation and rewards sitting with the discomfort. The prototype does not get to see what it started. The first worker on the first shift does not receive the medal given to the commanding general of the group that flew the 500th mission. The man who sat in a hallway for 3 hours does not appear in the post-war documentary. This is not a tragedy. It is simply the structure of how large things get built by many people across time, with credit distributed according to visibility rather than contribution, and with the original sources of ideas becoming harder to identify the more successful those ideas become. The P-47 Thunderbolt destroyed more enemy aircraft than any other American fighter in the Second World War, flew over 500,000 combat sorties, and demonstrated that the industrial capacity of a free society, fully committed and properly organized, could produce quality and quantity simultaneously at a scale that no adversary could match. Robert Woods, who never received a medal, proved that the most dangerous thing you can bring to a war is not a better weapon. It is a better process for building one. If you know a story like this one, a person whose name history misplaced an innovation that changed everything and credited nobody, leave it in the comments. These are the stories that deserve more than a footnote, because the most consequential things ever built were built by people nobody remembers. And the fact that we can still trace what they made, still fly the aircraft, their decisions kept in the air, still count the missions their work made possible, is the only monument most of them ever got. That is enough. It has to be enough. And in their case it was.